Welcome back after yet another long break. So this is going to be lecture 21. We are continuing part 3 of the course, which is going to deal with integers specifically. So the last few classes, what we were seeing the primality testing question, which is in some sense before one does a factorization thing, often the first thing that you want to check is, are there non-trivial factors at all? And this decision problem, it has a long history. We first saw the Miller-Rabin algorithm, which basically is like is based on what's called the Fermat test. Okay, and plus some Chinese remindering to help us make sure that even for numbers that happen to pass the Fermat test, you are still able to figure out if the number is prime or not. That was a Miller-Rabin algorithm. It's a randomized polynomial time algorithm. It's very simple to describe, and in fact, this is what is often used in practice. So mostly in practice, there are these two randomized algorithms. One is called the Miller-Rabin algorithm, and there is another algorithm which is called the Solovay-Strassen, which we didn't do in the class. Both of these are randomized algorithms, and mostly this is what is used. In fact, if you are willing to assume some mathematical conjectures called the Riemann hypothesis, etc., there is a de-randomization of these algorithms which you could use. So, but they are conditional. They depend on the fact that something called the extended Riemann hypothesis is true. But nevertheless, we saw this amazing algorithm of Agrawal, Kayal, and Saxena, which is sort of, I will say, based on the binomial theorem, or based on the binomial expansion or something, which is basically you're looking at x plus 1 whole to the n and saying that if n was a prime, then when I look at this mod n, I should only get x bar n plus 1. And then you use this as a test to come up with an algorithm. And this algorithm is also very easy to state, in the sense that the actual algorithm is quite short. The analysis is a bit more involved, and the running time is a little, I think the current best implementation of the Agrawal-Kayal-Saxena test is probably, something like log n par 5 sort of algorithm. Okay, which for large numbers may be impractical, but nevertheless. Okay, and
published from Kanpur, right? If I am not wrong.
Yeah. Manindra Agrawal is a faculty at Kanpur, of course, and Neeraj Kayal and Nitin Saxena were both BTech students at IIT Kanpur. So this happened it started as their BTech project, and after that, in the summer was when this result was proved. If I remember right, it's 2002. And then they joined for PhD at IIT Kanpur, and they've gone on to do several other fantastic things as well.
I probably heard that only one of them got PhD based on this paper.
No, that's not true. Firstly, this was, all of this is like completely irrelevant to the class. But okay. The point is, both of their PhD thesis has several other questions. In fact, the actual AKS primality test, there are just variants of the AKS primality test, different perspectives of the AKS primality test that's there in either of their theses. So let me proceed. So today, and this class and the next few classes, we are going to focus on the following factorization question. I am cheating a little bit here. What I'm describing as a factorization question is not what you normally think of as factorization. Normally, you'll say, I'm given a number n and I want to compute its entire prime factorization. But as we have seen earlier, if we have some reliable way in which we can get one non-trivial factor, we can just rinse and repeat and keep getting all the non-trivial factors, etc. So in fact, this is the problem we are going to focus on. I'm given a number n, and I am asked to compute a non-trivial factor if there is any. So we'll always assume that we are given a composite number, because if we are given a prime number, we'll be running one of the earlier algorithms. convince ourselves that the number is prime and just say bye. So we're going to just focus on the fact that I'm given a composite number, I'm told there are non-trivial factorizations, and we want to find. Okay. And if you have already started thinking about problem set 3, then you will also know that I might as well assume that this number is not a power of a single prime, because we have algorithms to do that efficiently. Okay. So obviously this is a very foundational problem in general. I mean, factorization is a very important question, but there is also a lot that rides on it. Okay. So I'll just say that, this is a problem that is actually believed to be a very hard problem by many. And I should add a sort of conditions apply sort of thing here, because I mean, there are actually a substantial number of people who do believe that factoring is perhaps in P, and we just haven't found an algorithm yet. And I mean, like very serious people who have good reasons to believe this as well. But there is a lot that sort of rides on the fact that we want factorization to be hard. So this is actually quite important, practically speaking as well, especially for crypto. Okay. I don't know how many of you have taken Aksharam's course on cryptography. I mean, I would highly recommend it. And there you would have seen that, sorry, was there a question?
No, I had taken.
Okay. So the point is, I mean, like, so there are a lot of crypto systems. I mean, okay, what do you want for cryptography? You want to be able to say that two parties, which are normally named Alice and Bob, they are sending messages to each other, and they want to do it in a way that an eavesdropper it's not able to figure out what the conversation is. So something underlying this must be preventing the eavesdropper from figuring out what the conversation is. So the very statement of saying that it should be hard for an eavesdropper to make some sense of this conversation is already underlying this sentence, is somehow saying that you're assuming that something is hard. Okay. And one useful problem which is assumed to be hard is the factorization question, and a lot of crypto systems are based on that. Okay, so let me very informally state what is called the factoring conjecture. Sorry, there is something. Oh yeah. Okay, Varun is just saying that crypto, we don't mean cryptocurrencies. So, but cryptocurrencies do use cryptography in them. Okay, let's throw these buzzwords and see how many views we get. So anyway, so the hardness of this factoring conjecture, this is a very informal way in which I'm stating it. It's a very imprecise way, but just to get my point across. Okay, so the general belief is the following, which is you say that you have a certain security parameter, which is, let's call it L. This L is basically telling you how much time is the adversary or the eavesdropper allowed to run it. So you are somehow talking about security when it comes to polynomial time algorithms that run in L time or something like that. Okay. So then the following task is believed to be hard. If someone picks a random prime, like a random prime from the first two parallel numbers and another random prime from the first two parallel numbers independently, and now builds this obviously composite number n, which is the product of p and q, and someone provides this n and says, okay, now factor it and show me. Okay, the belief is that there is no polynomial time algorithm to do this successfully. Okay, the precise statement is more about exactly what sort of distributions are there to generate these composite numbers, etc. But roughly speaking, you want to say that there is a reliable, there seems to be some reasonable way to generate composite numbers which appear to be hard for poly and L time algorithms to be able to factor. Okay, so that's the high level picture of what the factoring assumption is. And this is something that is believed, and a lot of crypto systems are based on this assumption.
Do we also want factoring to be hard for randomized algorithms?
Yeah. So by poly time, I'm being very, I mean, anything that you want to fight against, whatever you believe are the adversaries. So you want to say that those adversaries should not be able to factor the sort of numbers I'm building in the process. So that's roughly what it is. And this is used for the sort of public key cryptography systems or public key crypto systems, which in some sense it's a way of making digital letterboxes. Okay, so what do I mean by that? Like, I mean, there are post boxes that people have, like, and you can sort of say that, you know, by the way, my post box number is 107.1 or something like that. Okay, and this is something that you can announce to the world. You can put in your visiting card, put in your website, whatever, or something, and that enables anybody to send a letter to you. Okay, they just put the letter into your post box. But the only people who can read the letter are people who have the key to the post box. Okay, so that's roughly what you want to build. And the way this is done in the digital world is that, for example, if Alice is the party that has the post box, then Alice has two components of what is called their key. Okay, one is called the public key, which is exposed to the world. Like you inform people saying, you know, by the way, this is my public key. Anybody who wants to send me a message may use this public key to send the message. But Alice has hidden with herself a private key. Okay, and the private key is what is going to enable Alice to decrypt messages that are sent. Okay, so this is the rough setup. So there's some key generation protocol that lets them build public key and private key. And what we want is the following. There is some encryption algorithm which takes a potential message M and takes the public key of the recipient and returns a certain ciphertext. Now notice that anybody who knows the public key is therefore able to compute this encryption function. Okay, because it only needs whatever is the intended message and whatever is the public key. And in order to decrypt, what Alice is going to do is going to take the ciphertext that you got out of the message along with the private key, and you want that to be basically the inverse of the previous function. You want that to be able to recover what it is. And the idea is that without access to this private key, someone should not be able to figure out what M is from C. And you want to probably make this more precise. It's not just that I shouldn't figure out M exactly, I shouldn't even be able to get some information about M. It shouldn't leak any information, etc., but we are not going to get into any of that. Okay, but this is the general setup for what public key crypto systems are. Okay, and a very, very popular public key crypto system is what is called the RSA Crypto System, which is by Rives, Shamir, and Edom. Okay, so let me just describe what the RSA Crypto System is. Okay, the way Alice is going to generate her keys is she's going to choose two fairly large primes P and Q and set N to be equal to P times Q. Okay, now what is the size of Zn star? That is the set of numbers that are co-prime to N.
Phi of
Yeah, so phi of N in this case, what would it be?
So it will be
P
P
minus
minus
1
1 into Q minus 1.
Yeah, okay, Q minus 1. I'm assuming that P and Q are distinct because Alice definitely does not want to choose P and Q the same, because factoring such N becomes easy. So Alice is really relying on the fact that I'm going to make N public, but that is still not going to reveal what P and Q are. Okay, now the next thing that Alice does is Alice chooses a number E in the group Zn star. And the way this is going to happen is you just pick up a random number, check if it is co-prime to N. Otherwise, if it's not co-prime to N, pick one more, and you keep doing this. Normally, this E is chosen to be 3 or something. Okay, so there's some, you just try out and this is what you do. And because this is a number in Zn star and Zn star is a group, okay, there exists a number D such that E times D equals 1 mod N. Sorry, am I missing up something? Sorry. This is not what I want to do. I want E to be, what am I? Sorry. I want E to be co-prime to whatever, this phi of N. Okay. And there will exist some D such that E times D is equal to 1 mod phi of N. Okay, because of the fact that if E is co-prime to phi of N, then it means that your whatever Euclidean algorithm will tell you that there is some inverse, so you can compute this D. Okay, so this is the initial phase. And now what's the public key? The public key is just this integer n and the exponent e. Okay, and the private key is actually just going to be the integer n and this inverse exponent d. And if you want, you can add p and q, but p and q is not necessary for the decryption algorithm. Okay, is this clear?
Why n is a private key?
Sorry?
Why n is a private key?
I mean, n is public and private. I mean, like, I'm writing n in the private key also because this function I'm going to now define will use n inside. Okay, the way I have defined it is something that takes a ciphertext and some potential key and decrypts. And I'm just saying for decrypting, I will need to know what d is and what n is. So n is already public. So putting n in private is just more as a technicality for our definition. But it's just important that this d is hidden from the word. Okay. And what is the encryption going to be for any message m? You are just going to do m power e mod n. Again, this is a very vanilla version of it. Problem set 3 will tell you why what I'm suggesting is perhaps not the right way to encrypt things, but I'm just giving you the bare bones version of this. Okay. And for decrypting, it's just going to be c power d mod n. Okay. And I let you convince yourself that if it so happens that m and n are co-prime, which is going to happen with overwhelming probability, okay, then m power e power d mod n is actually going to be equal to m mod n. So therefore, you will recover m completely. And the hope is that just looking at m power e mod n, I won't know what m is. And there is a way to make it formal and somehow say that if you believe that the above factoring conjecture is true, then this is true. I mean, a lot of things need to be made precise, but this is the rough idea of what's going on. But notice that if for some reason the factors of n were known, then you know what p minus 1 times q minus 1 is. Which means, given this e, computing this d is something you can do as well. Because it's like running your Euclidean algorithm and just figuring out what the inverse of e mod phi of n is. So then this is no longer private. I mean, this is as public as anything else. So therefore, there's nothing that really distinguishes an eavesdropper from Alice, because anything that Alice can do, now the eavesdropper can also. So the entire setup that we have here appears to rely on the fact that given just what n is, I should not be able to figure out what p and q are. Or at least it must take me too much time to figure out what p and q are that I can basically safely say that, okay, no adversary in the world has this much time. So I will just choose the length of these numbers to be large enough such that in order for the adversary to break, I mean, the adversary perhaps needs more time than the age of the universe or whatever. So that's typically what you will set up your parameters large enough in the hope that there is no good way of doing this. And this is also why anytime someone comes up with a non-trivial factoring algorithm, and in fact, this need not even be a provably better algorithm or anything of that sort. Even if someone comes up with a heuristic to sort of say that, okay, I have some bizarre algorithm, it just appears to do factoring reasonably well. All such algorithms have far-reaching consequences because it somehow threatens your conjecture that you had above. You're somehow, all of cryptos, a lot of crypto systems that use RSA and so on, strongly rely on the fact that factoring is hard. And any such heuristic is therefore something that you need to take very seriously, because those are what are going to tell you, well, if I'm going to choose my private key, how large should these P and Q be? Like maybe around 10 years back or something, P and Q could just be 512 bits or 1024 bits or something. But nowadays, when you choose RSA, you basically end up choosing something like 2048 bits or 4096 bits or something. Or in fact, actually nowadays people just say that no, let's not use RSA, let's use other forms of crypto systems, because there are too many of these heuristics that appear to be doing reasonably well. And so maybe that threatens how good how much faith we want to put on the whatever validity of the assumption that we had that factoring is happening. Okay, so this is the reason why I'm just saying this to justify the fact that in this part of the course we'll be doing a lot of heuristics. We'll just roughly convince ourselves that okay, this appears to run in this much time. It seems reasonable or something, and we'll happily hand wave. Okay, whenever possible, we'll basically say, yeah, things should behave random and stuff like that, with really no justification. And the reason we are going to do this is because it doesn't matter as long as there is a small element of truth to it. It still has far-reaching consequences. In fact, let me give you an example of how important this is. There are people who just collect RSA public keys, various forms of these ends. They will collect it, and they just do a pairwise GCD among them. And the only hope, basically they're hoping, is that two different people who picked their private keys, which is P and Q, there is some decent chance that two people chose the same P. So this P will show up in the GCD. In fact, there are people therefore who do this. So it is important that when you choose your P's and Q's, that you apply a certain amount of randomness and that you don't fall for these collisions, etc., etc. So it's very subtle, and it's a lot of money lies on this. Because many of banking related stuff, etc., use RSA as one of the steps, etc. So this is something that you want to pay a lot of attention. So which is why in this part of the course, we are actually going to do some factoring algorithms. A lot of them might seem completely stupid, but it's to just get some edge over a brute force test. That's it. That's what we are going to try and do. Okay. So let's begin with algorithms, and I'm going to begin with the stupidest algorithm. Can someone tell me what is the stupidest algorithm for factoring? Okay, maybe not the stupidest, but a stupid enough algorithm for factoring.
After brute force.
Okay, so let's even write brute force. What is brute force?
Start just okay. So start with let's say just for D is equal to 2 to n or whatever.
Okay. Okay, if D divides n, return D. Okay, else return prime.
And there is some sieve kind of stuff, I guess, which can do.
So okay, so maybe I should probably put n minus 1 so that whatever. But the first thing is, okay, how far do I need to go until I'm sure that there are no factors?
Root n.
Okay, is it n by 2 or
root n?
It's root n, right?
Okay.
Right.
Sure.
So therefore,
sure.
Technically speaking, I can just go from 2 till about root n and just keep checking, if any of these things divide n or not. If it divides it, then I return that particular key. And if I haven't found a factor until root n, I know there are no factors. So yeah.
Box of root n basically.
Sorry?
Box of root n.
Sorry, what of root n?
Box means the greatest integer value.
Oh yeah. Okay, I'm going to be very sloppy with these things. Yeah, you probably need to take whatever the ceiling of root n or something like that. It doesn't matter. Okay. So what is the time complexity that this takes? Well, clearly the algorithm seems to run in time about order root n. I'm just going to ignore all polylog factors. Like the time that it takes to check if D divides n and all. This is minuscule in the grand scheme of things. So therefore, we are not going to care about this. Okay. So obviously this takes about root n time. And the question we are going to constantly keep asking is, can we do better? Okay.
So,
yeah.
If like, for example, if you check for 2, then if 2 divides n, we already, so we don't need to check for 4 and so.
Yeah. So, so basically you're saying that I might as well check for just primes in this range or something like that. Or maybe do some sort of sieving or whatever, but it's going to end up taking about root n time. We'll probably shave some log factors, but again, we are anyway ignoring those log factors. So just to make life simple for the rest of the rest of the thing, we'll focus on what we believe is the hard case, which is n is a composite number that's made up of 2 prime factors, and both of these prime factors are reasonably large. Okay, and that's really the hard case. And in fact, this is also the case we want to solve if we want to break RSA, because RSA will end up using these sort of n's, and therefore let's say we focus on just breaking that. Okay, so let's try to, just maybe try out a few things and see if we can somehow improve this square root n algorithm that we have. Okay, so suppose I just pick a random number from Z mod nz. Okay, notice that the number of numbers less than n, which are not co-prime to n, there's only about root n of them. So maybe like 4 root n or 3 root n, something like that. Because the only numbers that are not divisible by, that are sort of not co-prime to n, must be multiples of p or multiples of q. And if p and q are both roughly of the order of root n, well, there are only order root n multiples of p or q. So with very, very high probability, when I pick up this a, very likely it is going to be something that is co-prime. Okay, so I'm just going to approximate this to sort of say this distribution of this whatever sampling process of picking up a number a at random. I mean, if you're ignoring this, this sort of off chance that you end up picking something that is not co-prime to n, which is a very minuscule probability, then let's instead consider the following thing, which is we are picking up a number a, which happens to be co-prime. So it's in Zn star. Okay. Now, what do we know from Chinese remainder theorem? We know that this space Zn star, or in general the space Zn, is actually Zp star direct product Zq star. Okay. So this is just Chinese remainder theorem being used. So whatever this A was chosen, this A has a representative here, which looks like alpha comma beta. Okay, and it's just that for someone who doesn't know what P and Q are, I don't know what alpha and beta are. It's just that there is some representation. Okay, and the point is, choosing this A at random from here is equivalent to choosing alpha comma beta at random from here. Okay, so these two are just different perspectives. It's just one of them I seem to have more control over. The other one is like a representation that I don't really end up knowing. Okay, so here's what we are going to try and do. I'm just going to pick a lot of samples, A1, A2, blah, 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 till some AR. These are all independent samples from Zn star. Okay, now A1 has some representation. Let's call that alpha 1, beta 1. A2 has a representation, which is alpha 2, beta 2, etc., etc. And AR has a representation, which is alpha R, beta. This is equivalent to, so this is like Zp star cross Zq star. Okay, is it okay so far?
I didn't get, so why it is equivalent that getting A from Zn to Zn star?
Because of the fact that this is an isomorphism. This is an isomorphism.
That I got it. But you have given an equivalent signs between A belongs to Zn and A belongs to Zn.
No. I'm just saying that this experiment, okay, the chance that one of these random, so let's just imagine that A1, A2, blah, 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 till AR were picked at random from, let's say, Zn. So the chance that one of these AIs happens to be not co-prime to n is so minuscule. It's like 1 by root n or something. Right? So therefore, I mean, the chance that any of them happens to not be co-prime to n is small enough. So I'm just ignoring that.
Okay.
So everything that I'm saying, you might as well remove the stars and also say it's not a big deal. Okay, so maybe let me just remove the stars completely. And I mean, in case that actually confuses things, because the star is not helping me in anything. Okay. Now, so here is a question. So suppose it happens that right now I have picked up a bunch of A1 through ARs, but I know that there is a there is a representation in terms of the Chinese remainder theorem, which is made up of these pairs, alpha 1, beta 1, alpha 2, beta 2, beta 2. Now, suppose it so happens that the first coordinate in the ith guy and the first coordinate in the jth guy, somehow they happen to be the same. I mean, beta I and beta j could perhaps be different. I don't know.
That has to be right because it's isomorphism.
No. I mean, I don't know if these A1, A2, they're all distinct or something, right? I mean, I'm just saying if they were distinct, then they have to be different. Okay, let's just assume that, they're all distinct, for instance. But suppose somehow the first coordinates, two of the first coordinates happens to be the same.
Then the second coordinate should be same.
No, but why should the second coordinate be same?
Because you have taken the isomorphism, right?
I mean, so for example, it could be the case that alpha 1 is equal to alpha 2, but beta 1 could be different from beta.
And then those AIs would also be different.
Yeah, the AIs are different. Let's say the AIs were distinct things, but internally they have some representation where there's a first coordinate and second coordinate. It could happen that maybe the first coordinates are the same. Right? So, but I want to know, suppose you are told that I and J are two examples where the first coordinates are the same. How do you use this to get a factor of it?
Beta I minus beta j tells us something, right?
Sorry?
I mean, if we had a 0 in one of, like, if like 0 comma something.
Excellent. So how do you, once you know this happens, how do you get a number whose Chinese remainder representation looks like 0 comma something?
Would AI minus AJ work?
That's right. So then notice that P must divide AI minus AJ, because the Chinese remainder representation of this guy will basically be 0 comma beta I minus beta j. And if AI and AJ were supposed to be distinct, this is a non-zero number somewhere between, in this residue class of n. But I know for a fact that the Chinese remainder representation has the first coordinate being 0. And that can happen only if P divides this. So great. So which means that, once you find a collision in the first coordinate, you automatically know that if I took a GCD of AI minus AJ with n, I will pull out the factor P. Okay. Is this clear so far? So here's what we are going to do. It's an utterly stupid algorithm. Okay. So we are just going to run over 1 through R. We need to figure out what R is soon, but let's get to it when we get to it. And what we are going to do is we're just going to pick R samples. I'm just going to pick a uniformly random sample from 2 to n minus 1. Well, obviously, if I got lucky, and if this AI happens to have a non-trivial GCD with n, well, great. I just return whatever GCD I found. Okay. The interesting thing is every time I find a new thing, let me take a difference with all the previously found AJs. And if the GCD of this difference with n was non-trivial for any of them, I return the GCD. Is the algorithm okay so far? So we're basically going to ask, how large should R be so that I am guaranteed that, or not guaranteed, or that with high probability, or even this can even be heuristically, in a very rough estimate sort of a thing, that I expect to find a collision in the first coordinate. First is not important, first coordinate, second coordinate, it doesn't matter. Okay, in the Chinese remainder representation. Is the question clear so far? I mean, we have a template of an algorithm. We are just asking how many samples should I choose such that this if possibility is reasonably likely for this to happen. Okay, and this is something which is called the birthday paradox. This is something that you want to say that how many people should be in a class so that 2 people have the same birthday with high probability or something. Okay, so I'm just going to say I have R samples from some space M, and I want to know if I pick up R samples, how large should R be such that I can say that the probability that these guys are distinct are very small.
M plus 1?
M plus 1 is a surety because of pigeonhole principle.
Root
but But you probably want to say that no, you probably hit this thing very early. And in fact, this is why it's called the birthday paradox, because roughly if you have a class of about 24 people, the chance that 2 people have the same birthday is more than half. So 24 is like much smaller than 365. And that's the whole point of the birthday paradox. And let's just do this calculation. Okay.
Why it is paradox?
I mean, because somehow intuitively it feels like there are m possibilities. So for you to have a collision, it feels like you need to have linear in m many samples. But if you do a little bit of calculation, you suddenly realize that no, it's actually not linear in m, it's actually root m. It's like roughly root m samples is what you need for you to start seeing a collision. Okay, and that's why it's called a paradox, because the knee-jerk reaction seems to be that you probably need about m. Okay, so let's just do this thing. What's the chance that when I pick up r samples that they're all distinct? Now, I mean, I'm just going to write down. I mean, if people have, if people challenge this, I will explain. So this is just going to be m minus of r minus 1 over m. I mean, this is a chance that the first sample gives you something distinct, which is like, of course. And the second sample being distinct is like, I better pick up something from something I haven't picked up already. And this is the total probability that the r samples that I picked up they were all distinct. Okay, and this can be simplified as 1 into 1 minus 1 over m into 1 minus 2 over m, blah, 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 till 1 minus r minus 1 over m. And let the hand waving begin. And I'm going to basically say that each of these things, 1 minus x, roughly looks like e power minus x. Okay, this is again, I'm just, these are some approximations that people often do. And in this case, this is going to be e power minus 1 over m times e power minus 2 over m, blah, 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 e power minus r minus 1 over m. Okay, and the nice thing about going to exponentials is that product of a bunch of exponentials, the exponents all add up. So the exponent of e is now going to basically be 1 over m plus 2 over m plus 3 over m all the way till r minus 1 over m, which we know this is basically e power minus r into r minus 1 over 2. Okay, the actual thing is not important except that the numerator looks like an r squared. There is an m in the denominator. So the point I'm trying to make is that the moment r starts looking like, some, I don't know, large constant times square root m, this number is going to become much larger than this 2. So this probability is going to start crashing to 0. Okay, so basically I'm just saying that if r is reasonably bigger than square root m, then this probability is close to 0. Okay, so this immediately gives a following algorithm. So set r to be equal to, so okay, let's just see what should r be. So what am I looking for? I am looking for a collision within the alpha 1, alpha 2, alpha r sort of things, just the first coordinates. How many different values can the first coordinate possibly take?
P.
There's p of them, which means in order for me to see a collision in just the first coordinate alone, this r has to look roughly like, I don't know, something like order square root p. Okay, and again, we are not, I just said it with respect to the first coordinate. Had there been a collision in the second coordinate also, this would have been fine. Okay, so let's be a bit more precise and say that what I want to choose r is the square root of the smaller of the prime factors that this has. Okay, whichever was the smaller of the prime factors, roughly choosing r to be some large constant times the square root of that is already good enough. And notice that if I have a number n, one of its prime factors has to be at most square root n. So this is like order n to the 1 by 4. Okay, so therefore, basically they say that you set r equal to order n to the 1 by 4, and with high probability, there will be a collision in one of the coordinates. Okay, so therefore the above algorithm basically needs time which is order n to the 1 by 4. Okay, just this algorithm that I had. It's a for loop on the outside that goes for n to the 1 by 4 time, and then the rest of the algorithm is like very simple. Okay, so far so good.
Yes.
Now,
Like, what's the like weakest link in this like chain of steps? Like is this is this formally? I mean, this is still exponential.
yeah.
The
So good. They're all exponential, but we're going to try and improve this algorithm because, I mean, oftentimes what happens is the following. So if someone tells you that I have an algorithm that runs in something like, I don't know, 2 to the 30 time, like it takes 2 to the 30 steps or something like that. Often cases, what you can do is, if you have sufficient amount of hardware, you have access to some clusters, etc. You might actually be able to do this in some reasonable time. It's not, I mean, it's a little painful that it's taking so long, but it's not that bad. There is a different problem with this algorithm, which is I need to store these A's that I have found until now. Okay, and that takes up space. And in many of these instances, a time of n to the 1 by 4 might be tolerable, but a space of n to the 1 by 4 is just a complete, you won't be able to do this. You won't have enough space on most of your machines to be able to do this. So there is of course, n to the 1 by 4 is not a spectacular algorithm in any sense of the word. But I just want to add one additional thing, is that there is an extra weakness to this, which is that this is a space n to the 1 by 4. Okay, so let me just add here is that this is also that, but space is also order of n to the 1 by 4. Because I need to keep track of, okay, these are all the A's that I have found so far. And every time I pick up a new A, I'm having to do these differences and figure out if n has a GCD with any of them. Okay, and this is I'm not saying this is not a problem. Of course, this is a problem, but this is in some sense a bigger problem. So the first thing,
I guess I also wanted to know, is this like we have done some hand waving, but is there any hand waving that we cannot formalize? Like, can this be made into an actual correct algorithm, or is this going to be a heuristic?
No. This is a correct randomized algorithm. In fact, the only hand waving here I did was this, but there are ways to make it precise. I mean, there's an exact calculation you can do for the birthday paradox. I mean, the standard way to do this is using Stirling's approximation. You write this as a ratio of factorials, etc., and do that. But I just did the easy way out to just convince you that R being roughly root m is what you should be looking at. Yeah. Okay. So the algorithm needs n to the 1 by 4 time, but it also needs n to the 1 by 4 space. I tried to merge some sentences I had in mind. That's also something weird happened. Okay, so what we want to therefore do is like, okay, fine. Let's say we tell ourselves that n to the 1 by 4 time is something that I can tolerate. But can I be more efficient in terms of the space usage? Okay, and that's what we're going to do in the remaining time in today's class, and then I'll set it up for the next lecture. So we are going to do an aside, and it's this absolutely wonderful algorithm which is called the Floyd's cycle finding algorithm. In fact, I was looking at Wikipedia today, and it seems like, so Donald Knuth attributes this to Floyd, but it seems like there appears to be references to a very similar sort of algorithm from earlier. So it seems to be one of these folklore algorithms, but it's attributed to Floyd. And there is also other versions of these cycle finding algorithms by Brent and Gosper and so on. But I'll just mention this, and because this is often what is used in practice, though it seems to be the case that Brent's algorithm is a little faster. So let me set it up. Now we are going to, this is going to sort of suddenly look like one of these programming interview questions or something. This has nothing to do with algebra computation. Okay, so the way this thing is often set up is that you are given what is called a linked list. Okay, doesn't matter what this linked list is, you are given some structure where from every cell you have a notion of what is the next cell. Okay, and each cell has an index. Maybe this is index 7, this is index 3, this is index 42, and stuff like that. So it just keeps on going. Okay, but at some point what happens is that this cell might sort of suddenly, it might do this big loop, and it might just end up looping within itself. Okay, so I have something like, let's say, n cells, okay, with some cycle here. Okay, and what you have access to is, given a certain cell, you can ask me what is the next element in this cell, and I will tell you what is the next index that's there. If you ask me what is the next of 3, I will tell you 42. What's the next of 42? Whatever it is here. But it so happens that, maybe this number is like 17. And it so happens that the next of 17 and the next of 3 are both equal to 40. In the sense that there is a cycle present. And the goal is to find this cycle. More precisely, I want to know, where does the cycle start? Okay, so this is the task. I give you access to some linked list of this form. The fact that it's a linked list, etc., is not important, but this is usually how the programming question is stated. And you say that, you're told there is some cycle here. Okay, and you only have access to a next function continuously, and you want to find this cycle. Now, there's an obvious way of doing it, which is you just keep track of, just keep walking down the cycle. Just keep track of everything that you have visited so far. And the moment you see a collision, haha, okay, I found where the start of the cycle is. But obviously, this takes up too much space. Okay, and I don't want to spend that much space. So let's give some notation. We'll call whatever the number of steps to start the cycle. I'm going to call it T, because it's like the tail. It's like a tail that has been added to the cycle. And the length of this cycle, I'm going to call that L. And T and L are both things that I don't know. I don't know what T is, I don't know what L is. Okay, and we are basically trying to find out what is the smallest T and L, such that you have this thing that AT equals A of L plus T. Okay, where AI, this is A1, this is A2, etc. Okay, so I'm just curious, how many people have seen this algorithm before? In fact, this has many names. It's also called the hare and the tortoise algorithm, and so on. It's a spectacular algorithm. Okay, so let me just write down the algorithm. The algorithm is made up in 2 steps. Okay, there is an initial part which finds a collision, and then there is a part that finds the start of the cycle. Okay, and here is the thing. So X is going to be the tortoise, and Y is going to be the hare. Okay, and the hare is obviously faster than the tortoise, so it's going to move much more than the tortoise is. And here's what we are going to do. We are going to initialize X2. We are going to put the tortoise in step 1 and hare in step 2. Okay, and now we'll ask, does X equal to Y? Okay, if X is equal to Y, then I have found the collision already. We'll do something at a later point. But if X is not equal to Y, what do we do? The tortoise moves 1 step, and the hare moves 2 steps. Okay, so initially I'll be tortoise in position 1, hare in position 2. Then tortoise will be in position 2, hare will be in position 4. Then tortoise will be in position 3, hare will be in position 6, etc., etc. You keep doing this, and at some point you can imagine that this hare is going to lap around the loop and end up meeting the tortoise. Okay, so this is the algorithm. This is the part where they're basically going to, hare moves 2 steps, tortoise moves 1 step. And you keep doing this until X equal to Y. Suddenly they realize, hey, they're both in the same space. Okay. So, okay, let me not, rather than tell you more about this algorithm, let's just look at what has happened so far. Okay. So it was something like the loop was something like this. Okay. At some point, maybe you've gotten till here. Okay. This I is where the hare and the tortoise end up meeting. Okay. So that is when, what I mean is like when x is equal to y, say they are at, or rather this is after I steps. So what do you know? You know that x is equal to ai. Okay, and because the hare moves twice as fast as the whatever the tortoise does, this y is going to be equal to a to y. Okay, because that's how many times the hare would have moved. But of course, this a to y, there are repetitions involved. Okay, so which means that if this looks like, so I don't know, something like t plus let's say k1 times l plus an alpha, this looks like t plus some other k2 times l plus an alpha. That is, they both took this tail, which was of length t, went around the loop a certain number of times, and then went alpha many steps. Okay, now here is a question for you. So now, suppose let's say that we'll make the hare start here, okay, and we'll make the tortoise start here. And we'll tell the hare to slow down. Hey, only go one step at a time. Okay, so therefore the hare moves one step, tortoise moves one step. And then the hare moves one more step, tortoise moves one more step. What is the first point that they will meet? I claim that the first point they will meet is this. Can someone explain to me why that should be the case?
Because of the module, we are taking the mod, right?
Yeah.
So it might happen that two different will have a same representation in there.
Yeah, but I want a formal, precise proof. So think of it this way. The first part of the algorithm, where the hare was moving twice as fast as the tortoise was, at some point, the tortoise slowly took its time to come here. But on the other hand, the hare came here, and if the hare was allowed to, I mean, like if the tortoise was allowed to run just as long as it has already run once more, I give you saying, walk as much, you would have ended up doing something and come back to the same spot. So all I'm trying to say is that the time that it took for the tortoise to come here, if the tortoise had started walking from this step, okay, it would have come back to the same spot, because that's what the hare did, because the hare walked twice as much as the tortoise walked. Right? So therefore, if you now ask yourself, so there is a certain length that you have walked so far, which is this whatever t plus kl plus alpha or something. Had you started from here, you end up here. Had you started from here, you end up here again. So where would you, if two people were walking, starting from this point and this point, I mean, they eventually, you end up meeting here, which means one step before they must have met here. One step before they must have met here, etc., etc. Until this point, they must have met, but then this guy went here and this guy went here. So the first point they meet is actually going to be the start of the cycle. And that's what the second step of the algorithm is. The second part of the algorithm basically says, okay, now let's move the tortoise back to the start. Okay. And let's ask both the hare and the tortoise to just keep moving one step until they meet. And when they meet, you're at the start of the cycle and you say, the initial tail was of length t. Okay, is the algorithm clear? Is the description of the algorithm? Now notice here, at no point are you storing anything besides where is the tortoise currently and where is the hare currently. You don't need memory to get a sense of, where all has the tortoise been or where all has the hare. You just need 2 pointers in some sense. And okay, maybe 1 counter to figure out, what this tree is. Okay, it's a beautiful algorithm. So, but anyway, I mean, all we said was that, we'll run for a few steps until X and Y are equal. How large should that I be? Like, how many steps does the hare or the tortoise need to move until they end up meeting? I mean, obviously, if this I is too large, then the algorithm runs in too much time. Okay, so I'll let you, I'll just tell the answer. You can verify this. So if you take I to be the following number, which is T plus L minus of T mod L. Okay. Now notice that this is a number that is smaller than L because the residue will always be something between 0 to L minus 1. So this entire thing is at most T plus L. Okay. And you basically notice that T power 2, so convince yourself that basically AI equals A2I. Okay, or in other words, 2I minus I is divisible by L. So that will basically say that certainly at this point. So all I'm basically telling you is that the running time of this algorithm is no more than order of L plus T, which is basically the total number of cells in the linked list. Okay, and the space used is basically nothing. Or I'll just say epsilon. I mean, you're basically keeping track of just 2 pointers and maybe 1 counter. And these are all things which are stuff I'm going to ignore. I mean, we are fighting against n to the 1 by 4th. Now I'm telling you that the space used is like order log n. So these are all. Okay, so this is basically just 2 pointers plus 1 count. Okay, so this is there. So now let's ask ourselves, how are we going to use this for factoring? Okay, we are going to basically do something like cycle detection, which is like something like collision. Like the next function has a collision. I want to find that thing. So here's what we are going to do. And this is called, this is the algorithm that we'll soon, I'll define something called the next function. In fact, the define is more like I'm going to tell you something with no reason to believe this is a good next function, but it's just something that works. It's a heuristic. Okay, so what we are going to do is the following. I pick an A at random. Okay, that's the starting point of the loop. Sorry, this should have been A1. Okay, so the tortoise is at the starting point and the hare is currently 1 step away from the tortoise. Okay, and basically what I'm going to do is the tortoise is going to move 1 step, the hare is going to move 2 steps, and I'm going to keep checking, does X minus Y, does it have a non-trivial factor with N? If it does, I of course return the GCD. If it doesn't, I just keep repeating this. And at some point, I mean, this while true, you just make sure that, if you haven't found something for too long, you just exit. Okay. And what's the idea? So the idea is that think of the following loop in your head where I actually have A1 mod P, where P is one of the prime factors. Okay. The next function, whatever that A2 was, now that is A2 mod P. And then it goes to A3 mod P, etc. Which means at some point there is going to be a loop. Okay. And you want to find 2 different AIs. You want to find an AI and AJ such that AI and AJ are both the same mod. Okay. And once you know that they are the same mod P, this GCD will give you something non-trivial. And you're just hoping that when mod p things are the same, there is no reason for mod q things to be the same. So hopefully, you actually get a non-trivial factor. And this algorithm is called, so basically all I'm saying is that if AI is equal to AJ mod P, then P divides AI minus AJ, which implies GCD of AI minus AJ, and N, this is not equal to 1. Okay, and the heuristic that is used is that this next function, the next of any A, is just defined to be A squared plus 1 mod N. It's just some function. I mean, I give you a number, I need to tell you what is the next number to go to. And the one that is used in practice is just some A squared plus 1 mod N. In fact, there is no reason to think that A squared plus 1 mod N is a good next function to use. But I mean, it just seems random. It seems like as if you end up going to something that seems random. Okay, there's no good reason for it. The general belief is that somehow if you pick A, I mean, somehow looking at A squared plus 1 mod N still appears to look random, somehow the Pollard's row. So this algorithm still continues to go. By the way, this entire algorithm is called the Pollard's row algorithm because of this shape. That this loop sort of looks like the Greek letter rho. Okay, and once again, the number of different residues that we have, there are a number of residue classes mod T. So therefore, the length of the tail plus the length of the loop, etc., is going to be at most P. So the total time taken is once again, it's going to. Okay, how do I put it this way? So if you believe that if I start with a particular A, and then I go to the next A being A squared plus 1 mod N, and if you believe that's like a random number, just mentally tell yourself that it's like a random choice that you take. Okay, and you keep doing this again and again and again. Okay, roughly speaking, you expect to find a collision in about root n steps, or rather root t steps. Same birthday paradox. If you believe that this is like a random thing that is happening, then roughly the collision should happen in about root n steps. Sorry, I keep saying root p, because you're looking at the residues mod p. So here is an algorithm that heuristically takes time about, again, whatever, the square root of the smallest prime. Okay, and the space complexity is almost nothing. Basically 2 pointers. And this is called Pollard's row algorithm. And of course, it's a heuristic because there's no reason to think that, somehow A squared plus 1 as a function of A is somehow like a randomly generated new sample or something. It's clearly correlated. But in practice, it seems to do quite well. So Pollard's row is quite effective if people are using, numbers of the order of something like 100 bits or 200 bits. And you want to factor those sorts of numbers. And for fairly smallish number, Pollard's row is actually quite effective. So again, this is order of n to the 1 by 4. Okay, it's a little bit hand wavy, but the algorithm is extremely simple to describe. This is the algorithm. Okay, you just replace next by whatever, something like A going to A squared plus 1 mod N, or you choose your favorite function. It doesn't seem like one is better than the other. Okay, so good. So at least we have gotten to a point where I now have an n to the 1 by 4 algorithm, and the space complexity is actually something that is tolerable. Okay, now obviously the next question we are going to ask is, can we do better than this? Is there a better algorithm? And now I'm going to sort of set up the stage for what happens in the next few lectures. And in fact, this is how almost all modern factorization algorithms, it's based on the following trick, which we will try to what is the word for it, which we will try to somehow make sure it happens, to find these things. I mean, these sort of wishful hopes of finding numbers of a certain type, we will see how to find these numbers. Okay, and this method is sort of referred to as the congruence of squares method, and it dates back to Krejcik in the 20s. Okay, and the idea is the following. Okay, the goal is eventually going to be, I want to find two numbers alpha and beta, which are not plus minus each other, such that somehow their squares are the same model. Okay, and this particular step is what is called the congruence of squares. I want two different, potentially different squares to be congruent mod n. Okay, now, okay, how to find this is something that we'll have to figure out in the next couple of lectures. But let's first ask ourselves, okay, even if you did find something like this, what is that supposed? I mean, like, how is this supposed to help you? Okay, and the key point is that this means that alpha squared minus beta squared is zero mod n. And the left-hand side factorizes nicely as alpha minus beta into alpha plus beta. Okay, so which means if n divides this product, okay, you're somehow hoping that one of these separate factors, I mean, obviously one of them must have a non-trivial factor with n, and hopefully they are non-trivial in the sense that it's not equal to n. I mean, if alpha is not equal to plus minus beta, there will be non-trivial factors that you would find. Is this okay? I mean, has it been okay so far?
Maybe I don't know if I'm a bit lost. Like some alpha and n minus alpha, that would work.
No. N minus alpha will again be minus alpha, right?
I mean,
so I don't want to choose those, but I want a different, I mean, some non-trivial versions of alpha and beta, such that alpha squared happens to be equal to beta squared. Okay, firstly, it's unclear why such alphas and beta should even exist, but I will let you think about it. Again, think in terms of Chinese remainder. Okay, so
n is composite. So.
Because n is composite, there will be non-trivial stuff, and we are trying to find some example of such a non-trivial congruence. Okay, once you find a non-trivial congruence, I mean, you then take a GCD of alpha minus beta with n and alpha plus beta with n, and hope that one of them is going to give you one of the factors. Okay, and this is how almost all modern factorization algorithms proceed. This is the task you're trying to solve. You want to find alpha and beta. Okay, maybe I should not have written Zn, because different modern algorithms look for these alphas and betas in some suitable worlds. Okay, but the task eventually comes down to, I want to find alpha and beta such that alpha squared equals beta squared. Because once you do this, you can somehow extract out a factor from alpha and beta. Okay, so let me just say that the current best factorization algorithm we know, and again, by best, what I mean is this is a heuristic. I mean, like, we'll make a lot of wishful hand waving in the middle, assuming that these hand wavings, etc., make sense. Then the running time of the algorithm is some expression of this sort. Okay, I'll ignore this thing because this is a lower order term. But the point I want to make to tell you is the following, which is that notice that this is smaller than n to the delta for any constant delta greater than 0. Because n to the delta will, so this is equal to, what is this equal to? This is like 2 to the delta log n. Right? Because n to the delta is the same thing as 2 to the delta log n. So here the exponent is delta times log n, whereas here the exponent is log n to the 1/3. Right? For as long as delta is any constant, when n grows larger and larger, this obviously grows much faster than this does. So therefore, this running time is what is, it's a sub-exponential algorithm. It's smaller than n to the delta for every delta, for every constant delta. So right now we were putting in so much effort to go from square root n to n to the 1/4 or something. But I'm just trying to point out that there are algorithms which are better than n to the 1/100 or n to the 1/1000, etc. Okay. And this is the current best algorithm, and this algorithm is called the number field sieve. I don't know what this, I don't know how to spell sieve. What is it, SIEVE or SEIVE?
I think it's I first.
Yeah. By the way, that rule doesn't work. I hope you have seen this amazing QI episode on that. Okay, but SIEV does sound, look right. Okay, but the number field sieve is something that is a little complicated, and this is something that we won't do in class because it's a lot more involved. But what I do plan to do in the next few lectures is do a weaker algorithm, which is called the quadratic sieve. Okay, which achieves the same thing. Instead of 1/3 and 2/3, it achieves half and half. So this is like a little slower than what I have written above, because I mean, here this was like log n to the 1/3 here, whereas it's like log n to the half. But nevertheless, this is also faster than n to the delta for every choice of delta. Right? So this is the algorithm that we will see hopefully in the, I mean, we'll have to build up a few tools before we see this. And over maybe the next couple of lectures or something, we will see a full description of the quadratic sieve, and then we'll really start optimizing various constants, because that will tell us whether we can handle 512 bits and stuff like that. So, so we'll try to optimize the constants as much as possible. Okay, so I mean, there's not much point in starting something else right now in the last about 15 minutes that we have or something. So maybe this is a good place to just maybe take questions and break, and we can meet on Thursday and then start the quadratics. So are there any questions?
Like both these sieve methods are heuristics.
Yeah. So it uses some bounds on something called smooth numbers, and the bounds on smooth numbers are actually precise, which will basically say that if you pick a number at random, the chance that it is smooth is going to be with this probability. But very quickly we will start saying that, okay, I'm going to start picking numbers by doing a squared plus 1, etc. And I'm just going to assume that whatever was the right density that we had for smooth numbers, that continues to apply. So we'll start making these sort of hand wavy statements. And it's just that it seems to be the case. I mean, like, primes don't seem to be following any nice algebraic properties. So it seems like, it does look random from the point of view of this algorithm, but we don't have any way of making these things precise right now. Okay, so in that sense, it's going to be heuristic. Yeah.
Like, what's the best correct algorithm that we know?
I mean, provably correct algorithm.
Probably.
So there is an algorithm that runs an n to the, I think, 1/5 time or something. Like there is a deterministic n to the 1/5 time algorithm. In fact, it was fairly recent. I'm forgetting the names of the authors. I think it's an n to the 1/5 algorithm that we have, which we know is provably correct. But many of these things are just heuristics. But they're very clever heuristics. I mean, the techniques that go into it are quite nice. Yeah, so we either do this or just collect public keys and keep taking pairwise GCD and hope that something shows up there. Yeah. Okay, so if there are no further questions, then let's just break now. We break a little early, and we'll meet again on Thursday, and we'll see. We'll start with the description of the quadratic sieve and some of the tools that we need for it. Okay, cool. Let's end stream.